Chapter 7, we're going to focus on solutions. Solutions are homogeneous mixtures made up of two or more substances. Now, if you recall from previous chapters, homogeneous solutions, homogeneous means that it looks uniform throughout, so our eyes don't pick up any particles or anything like that. And it's a mixture, which implies it's two or more things mixed together. Solutions consist of what we call the solvent and one or more solutes. So if we look over here to the right, the picture they're showing, the water is the solvent and the salt is the solute. The solute are the substances present in lesser amount, and the solvent is the substance present in greater amount. So those are two definitions which are good. Another one that's sometimes helpful is that when you are dissolving a solid in a liquid, the solute is the solid that's going to disappear, and the liquid, which causes the solid to disappear, is called the solvent. So that's another way to look at it that's sometimes helpful. The solution is defined then as the solute and the solvent once they're mixed together. Some properties of solutions: well, their composition is variable. That should be implied because I told you that they were mixtures. And if you remember, one of the properties of a mixture is two or more substances that you can vary the composition. So you can do that with a solution. You can dissolve a teaspoon of sugar or maybe 5 teaspoons of sugar. The solute and the solvent may be separated by physical methods. So once again, that's another definition of or property of our mixtures. You can separate mixtures by a physical method. In a solution, the solute particles are between 0.1 and 1 nanometer in diameter, and they're uniformly distributed among the solvent molecules throughout the solution. So basically, once again, it's homogeneous, it's uniform throughout. The solute particles do not settle out. So you can make some salt water, set it aside, and come back a year later, and the salt is still going to be dissolved in the water, assuming that you had put a lid on it. Solutions have the same physical and chemical properties throughout because they're uniform throughout. Solutions are transparent to light. So although they may be colored if the solvent is a liquid or a gas. Let me rephrase that. So solutions are transparent to light if the solvent is a liquid or a gas. So the nature of solutes in the solution. So the solutes spread evenly throughout the solution. They cannot be separated by filtration because the particles are so tiny. That 0.1 to 1 nanometer in diameter is so tiny that it's going to just go through any filter paper that we have. The holes are just too big in the filter papers. However, they can be separated by doing evaporation. You can evaporate off all the liquid and you'll be left with the solute on the bottom of your beaker or container. The solutes are not visible. However, they can give color to the solution. So if we look at this picture over here, they start off with a graduated cylinder and they put some copper sulfate crystals on the bottom, and you have water on the top. Over time, those crystals are going to start to dissolve, and after a certain amount of time, the molecules or the particles are going to be uniformly distributed throughout. And if you look at the picture, the copper is giving this solution a blue color. So sometimes colored, sometimes not, but definitely transparent to light. So even if it's a blue color, you should be able to read words behind it and things like that if the color is light enough. Here are some examples of some common solutions. So the first one is talking about a solution of a gas dissolved in a gas. And the example I have for you is air. And air is mainly nitrogen and oxygen. There's small amounts of other things, but if we just focused on the oxygen and nitrogen, we would say that nitrogen is the solvent, because remember, one of our definitions of the solvent is it is the component in greater amount, and oxygen is only present in about 21% of the air, so it would be the solute. Here are some examples of liquid solutions. So we have the 3 different kinds. You can dissolve a gas in a liquid, another liquid in a liquid, or a solid in a liquid. So an example of a gas in a liquid would be soda water, or pop for that matter, where you put carbon dioxide solute in the water solvent. A household ammonia, if you clean with ammonia around your house, it's really ammonia that's been dissolved in water. And ammonia is a gas, so they put some ammonia gas into the solvent water to make the household solutions. An example of a liquid in a liquid would be vinegar, where they take a solute of acetic acid and dissolve it in water, and water would be the solvent. An example of a solid in a liquid, seawater, so just sodium chloride dissolved in water. or tincture of iodine, where you take iodine, which is a solid, and dissolve it in alcohol. So in this case, alcohol is the solvent. A couple examples of solid solvents, and you could either dissolve a liquid in a solid or a solid in a solid. So this is showing, you can actually do gases in solids too, but I've got this example of a liquid in a solid would be dental amalgam, where they put liquid mercury into silver, and they make this amalgam for your dental fillings. An example of a solid in a solid, I've got two examples here: brass, where you mix zinc and copper, and steel, where you're mixing carbon and iron. And once again, your solute and your solvent is determined by which one you have in greater amount or lesser amount. So what happens if the size of the particles mixed in with the solvent are larger than 0.1 to 1 nanometer? Well, that's going to bring us to two other types of mixtures. The first one is a colloid, where the diameter of your particle is between 1 and 1,000 nanometers. So it's a little bit bigger than the particles in a solution. An example of that would be soapy water. Your soap molecules fall in this range of size, and your soap molecules can get dispersed within the water, and that'll bring us to something we call a colloid. And then the other type of a mixture we have is called a suspension, and in a suspension the particles are greater than 1,000 nanometers. And the example I have for you is a stirred up mud puddle. So if you took a mud puddle and you stirred it up and you got some of those big mud particles that had been on the bottom and you got them to mix up into the water, that would be called a suspension. Talking a little bit about scattering light and the differences between a solution, a colloid, and a suspension. It turns out that the particles in a solution are too tiny to scatter light. The light just travels right past your solution particles without scattering any of the light. However, for a colloid or a suspension, the diameter of the particles is big enough that when the light hits the particles, it scatters the light. So here I've got a picture where I've got, in my first container here, I have a solution, and the other container, I'm not sure, it's either a colloid or a suspension. I'm suspecting it's a colloid, but they're shining a laser through it. And if you notice, the laser you cannot see through the solution because the particles are too small to scatter the light. But in a colloid or a suspension, you'll actually see the laser going through. Sometimes the solution has big enough particles that the whole solution, as light goes through, the whole solution looks opaque. So here is a summary of those three different mixtures that I want you to know about. So in a solution, if we focus on the particle size, the solutions have a diameter of 0.1 to 1 nanometers, colloids are 1 to 100 nanometers, and a suspension, the diameters are anything bigger than, I hope I said 1,000, anything bigger than 1,000 nanometers. Colloids is 1 to 1,000 nanometers. Up here it's saying colloids are also called dispersions. So if you hear that word, a dispersion, they're referring to a colloid. Do the particles settle out upon standing? Well, if we're focusing on our solution, just think about the sodium chloride, salt in water. That salt is going to just stay in solution. So the particles are not going to settle out in a solution. They're not going to settle out in a colloid. An example of a colloid I can think of is milk. So if you have a glass of milk and you set it out for a day or two, the particles in the milk are not going to fall out of solution and fall to the bottom. However, a suspension, they are going to fall out. The particles are just too big to stay suspended. And like at the example of the mud puddle, the stirred up mud puddle, you let it sit for a little bit and all those mud particles will settle to the bottom and you'll be left with clear water on the top. Focusing on particles being separated from the solvent by using filter paper, well, the solutions in the colloid particles are too small. They'll go right through the filter paper. But you can separate a suspension by filter paper because they're big enough that the filter paper will filter out. Focusing on the behavior with light, solutions are transparent to light. They do not scatter light, but colloids and suspensions will. So those are a couple, several things to kind of memorize to help you decipher between whether I'm talking about a solution, a colloid, or a suspension. Focusing a little bit on water, we know most of this, but water is the most common solvent because of its unique properties. It's a polar molecule, which hopefully we remember that from chapter 4. It forms hydrogen bonds between the hydrogen atoms in one molecule and the oxygen atom in a different water molecule. So focusing here on the water molecules, if I look at my first top water molecule, the oxygen in that one is going to hydrogen bond to a hydrogen in a neighboring one. This hydrogen is going to then hydrogen bond to an oxygen in neighbor 1. So I think we're pretty familiar with that. Solubility is defined as the maximum amount of the solute that you can dissolve in a specific amount of the solvent. It's usually expressed in how many grams of solute you can get dissolved in 100 grams of water. So you're often going to see the unit as being like 25 grams of this compound in 100 grams of water. Here is an example of some compounds. It's the solubility, which is the maximum grams of the solute you can have in 100 grams of water. Notice that in my first column I have the different types of solutes, but in the middle column I have how much will dissolve at 20 degrees Celsius, and then in my last column it's 60 degrees Celsius. So the solubility of compounds is affected by the temperature. So if we look at sodium chloride, we can expect to get 36 grams of sodium chloride to dissolve in 100 grams of water if the temperature is 20 degrees. If we heat up the temperature to 60 degrees, it looks like we can get 1.3 more grams to dissolve. Potassium bromide, there's some data. Look at the potassium nitrate is actually very temperature dependent. At 20 degrees Celsius, you can only get 31.6 grams to dissolve. But if you heat it up to 60, the solubility increases to 110.6 grams per 100 grams of water. Any others I want to focus on here? Silver nitrate's pretty interesting in how soluble it is. You can get 222 grams of it to dissolve in 100 grams of water. That's pretty impressive. And once again, it's very temperature dependent. Barium sulfate here, you can see is barely soluble. In fact, for all practical purposes, a scientist is going to say that barium sulfate's insoluble. You put a big chunk of it in, and it's, you're not going to notice much of it dissolve, because very few grams dissolve in 100 grams of water. A saturated solution is going to contain the maximum amount of solute that solvent can hold. So you're not going to be able to dissolve any more solute. The saturated solutions will have undissolved solute at the bottom of the container. So if we look at this picture here, I can walk into a room and see a beaker that has some solute on the bottom and say, oh, this must be a saturated solution because some of it is undissolved, assuming that enough time has occurred that it would have dissolved. And it looks static. I would look at this beaker that's been sitting out for a long time, so it's had lots of opportunity to dissolve, and it looks like nothing's happening. But on the molecular level, it's actually very dynamic, where some of the crystals are still dissolving, but for every crystal that dissolves, some more are going to precipitate out. So you always have this dissolving, precipitating cycle going on in a saturated solution. If the solution's unsaturated, then it's going to contain less than the maximum amount of solute. You're still going to be able to dissolve more solute in it if you want. So focusing on the picture here, there just is not very many solute particles floating around in your unsaturated solution. The water can still hold more. So here's a learning check. At 40 degrees Celsius, the solubility of potassium bromide is 80 grams per 100 grams of water. Identify the following solutions as either saturated or unsaturated, and then explain. Now, there's several ways to set up these problems. And these ones, that's not what I wanted to do. I wanted to get my pen. That's what I wanted. These ones right here, you could almost do in your head, but I'm still going to show you how I would set them up. We are trying to decide. So I've got 100 grams of water, and I'm told that the solubility is 80 grams of potassium bromide will dissolve in 100 grams of water. So if I have my 100 grams of water and I only put 60 grams of potassium bromide in, is that considered saturated or unsaturated? Well, I'm not even going to set this one up. This one we can definitely do in our head. 100 grams of water can hold 80 grams. I only put 60 grams in, so it's going to be unsaturated. And the reason why is because it can hold 80 and I only put 60 in, which means that the water can still hold 20 more grams if I wanted. The next one, I'm going to try to add 200 grams of potassium bromide and 200 grams of water. So what I would probably do to set this up is I would say, well, I know the solubility is 80 grams of potassium bromide in 100 grams of water. So that's the solubility they gave me. And I would set up a ratio. And I would say, well, if 80 grams dissolves in 100, how many grams can I expect to dissolve in 200 grams of water? And if you cross-multiplied, or however you would solve this for x, you would find out that I could get double the amount. I should be able to get 160 grams to dissolve in 200 grams if I can get 80 and 100. Well, I've put 200 grams of potassium bromide in, so I've actually added 40 more grams than what the water can actually hold. So this one right here is going to be saturated. And there'll be 40 grams on the bottom of my beaker if I added 200 grams. This one right here, once again, I would set it up and I'd say, okay, I'd start off with my solubility. They tell me that I can get 80 grams of the potassium bromide to dissolve in 100 grams of water. And I want to know, okay, well, how many grams of potassium bromide can I get if I only have 50 grams of water? Well, we can kind of do these in our head, but some of them might be more complicated where you actually have to do your cross-multiplying if you set up the ratio way. So if I only have half the amount of water, so I can only have half the amount of the solute. So in this case, X is going to be 40 grams. So according to the solubility, I can only get 40 grams of potassium bromide to dissolve in 50 grams of water. Well, the problem is saying that you add 25 grams of potassium bromide. Well, that is less than the saturation. Saturation would be hit at 40 grams. So this one is unsaturated because you added less solute than what our saturation point would be. So for saturated solutions of solid dissolved in water, so if we put some solid in water, if more solute is added, the excess is just going to fall and remain on the bottom. Because we start off with the saturated solution, I add more solute, it's just going to fall to the bottom because the water can't hold anymore. If enough water evaporates from an unsaturated solution, so now we start with a solution that's unsaturated, but if I leave it out for a while and I let the water evaporate, at some point I'm going to reach the point where it is then saturated. And if I allow it to continue to evaporate, then I'm going to start seeing precipitate fall to the bottom. Some of my solute will settle out. That's how this principle is how a lot of people grow crystals. So for example, if you were going to grow alum crystals, you could make a saturated solution of alum. So you start off by dissolving a lot of alum in the water, and you would suspend a string into that solution. And you would set the solution aside for several days, and what's going to happen is crystals will start growing on the bottom of the string. As water evaporates, the crystals have a way of wanting to grow once you've given them a seed crystal. So the string kind of acts as a seed crystal where it's a starting point for when the solution starts to become saturated and more liquid evaporates, and it's going to precipitate out. It tends to precipitate out on the string versus just floating to the bottom. So what you do is you leave it for several days and you wait for all of the excess alum to precipitate onto the string, and then you can remove it and you can make up another saturated solution and let it cool and put it back in, and you can end up growing some pretty big crystals doing this method. Needle-like crystals of uric acid will form in cartilage and tendons in your soft tissues, leading to this painful condition called gout. If the serum in your blood vessels is saturated in uric acid, well, it's going to precipitate if you get past that saturation point. And one of the places it precipitates is in the cartilage and tendons, and they end up growing as like needle-like crystals. So that's the shape of the crystals of uric acid. And it's pretty painful, I hear. I've never had it, but this picture looks like it's pretty painful. Kidney stones are crystals of calcium phosphate, calcium oxalate, or uric acid that form because the saturation point has been exceeded. So here they're showing some kidney stones in the kidney, and then when it becomes real painful is when the kidney stones start traveling out through the ureter. Gallstones are crystals of cholesterol. So if you reach a saturation point of cholesterol and it needs to precipitate out, it'll often precipitate out as gallstones in the gallbladder. So there's some different factors that'll affect the solubility. So the three we're going to focus on is the polarity of the solute and the solvent. The next one we're going to talk about is the temperature and how temperature affects the solubility. We've talked a little bit about it. And another thing that'll affect the solubility is pressure. If we're talking about trying to dissolve a gas in either a liquid or a solid, the pressure of that gas is going to be pretty important. So focusing on that first one, the polarity of the solute and the solvent, there is a rule of thumb out there that chemists often use that'll say likes dissolve likes. And what that means is that your polar solutes tend to dissolve in polar solvents. And non-polar solutes dissolve in non-polar solvents, and then you get where polar and non-polar don't mix. So if you talk about, you hear that saying oil and water don't mix, well now you know why. Water's polar, oil's non-polar, and polar and non-polar don't mix. So you get those two different layers. Here's an example of likes dissolve likes. I'm starting off with a test tube where I put some water, which is polar, and I add in some dichloromethane, which is another liquid that's non-polar. And it turns out, well, actually, why don't you tell me which one is more dense, the water or the dichloromethane? And I'm hoping you say that the dichloromethane is more dense because that's the one that sunk to the bottom. So we have this test tube. We add in the second beaker or test tube here, B. They've put in some iodine molecules. Well, iodine is nonpolar. Iodine's unique in that it kind of breaks this likes dissolve rule, and you can get iodine to dissolve in the water or polar solvents. That's how we get our iodine tincture. If you have ever had iodine spread on your skin before they give you a shot or something to disinfect, that's iodine dissolved in alcohol. So you can get iodine to dissolve in a polar solvent, and it ends up being brown when that happens, but it prefers the non-polar solvent. So when you put dichloromethane in here, the iodine might be a little bit in the water, but it's going to prefer to be in the dichloromethane. And then you get this pretty purple color iodine in a nonpolar solvent. Here they're putting nickel nitrate, and you want to be able to look at an ionic compound as being very, very polar. Because remember, you have the cation and the anion, which are completely charged particles, and you don't get more polar than that. So they're putting an ionic compound in the test tube that has water and dichloromethane, and since it's polar, it's going to dissolve in that top layer, the water. Focusing on how ionic compounds dissolve in water, we're focusing on sodium chloride here. And on the surface, so they've put some sodium chloride in the beaker. And what we have is these crystals of sodium chloride, which are very, very polar, and the water's polar. So water is going to be attracted to the cations and the anions. And they're actually going to be plucking off the sodium ions and the chloride ions one by one. And when they pluck them off, they end up doing something that we call hydrating it, where the water molecules will surround the cations and the anions. And as you can imagine, if you have a sodium ion, the waters are going to flip themselves around to where the oxygen is that partial negative oxygen is facing the sodium cations. And if we focus on the chloride anions here, the water will flip themselves around to where the partial positive hydrogens are close to the chloride. So that's what's going to happen. As you're dissolving the sodium chloride, the water is going to come and pluck off your cations and your anions, and they're going to solvate them or hydrate them. But at some point, you're going to use up all your water molecules, where all your water molecules are being used to surround the cation and the anion. And if you put more salt in, you can't get any more to dissolve. So the sodium and chloride ions are hydrated in the solution with many water molecules surrounding each ion. Here is how we write an equation to summarize the dissolving of a compound in water. This is just one way of doing it. But when sodium chloride dissolves in water, the reaction can be written like this, where you're writing water over the arrow, because it's not really a reaction with water. The sodium chloride's not going to react with the water. It's just going to dissolve in the water. And the symbols here, the S is telling us that I start off with solid sodium chloride. I put it in the water, and now what I have in the water are my sodium cations and this AQ symbol, which I talked about a while back, but it means aqueous. And so when a scientist sees this, they say, oh, okay, those sodium ions are hydrated with water. And my chloride ions are hydrated with water. So that would be the separation of your ions. I know this is a wordy slide. It's just a pretty cool concept. So I'm going to just kind of summarize it, but I recommend reading it. It's pretty interesting. But the strong ion dipole attractions, between water and a salt. Now, I'm not sure I've described a salt to you before, but I know we're used to salt being sodium chloride because that's our table salt, but a chemist is going to refer to a lot of ionic compounds as salt. So, anyway, when you have an ionic compound and water interacting, that's where we get that ion dipole attraction. So a strong ion dipole attraction between your polar water and salt can be used to explain why water is drawn out of cells when there is a higher concentration of salt outside the cell membrane. So that's going to be used to explain why you don't want to drink salt water to quench your thirst. Okay, so if you do, say you drink a lot of salt water, you're out stranded on your ship and there's no fresh water, so you start drinking the seawater. Well, what's going to happen is when you have a lot of the salt water is the water inside your cells are going to rush out of the cells and into the salt water solution because it's going to try to dilute it and hydrate all the sodium ions and chloride ions. And so that's going to dehydrate then the cells. And it's also going to cause problems to the kidneys because that's where all your concentrated salt water is going to go. So you might have the kidney failure. So that's kind of focused on how ionic compounds dissolve in water. Well, why is it then that we can get some molecular compounds to dissolve in water? So for example, we're all familiar with the fact that sugar can dissolve in water, but sugar is not ionic. Sugar is molecular. And so if we look at the structure of sugar, it might help us out. So sugar actually has a lot of OH, oxygen and hydrogens bonded to the outside of it. And what do we know about when we've got a hydrogen bonded to an oxygen? And I'm hoping you'll say that it can hydrogen bond. It's very polar if you have oxygen bonded to hydrogen, oxygen, if hydrogen's directly bonded to nitrogen, oxygen, and fluorine, that means that molecule can hydrogen bond. Well, we have a lot of hydrogen oxygens in sugar, which means it's very polar. And so it's going to be very attracted to water. So it's going to be the same sort of situation where the water is going to come and pull off all your sugar molecules. So why don't polar and nonpolar mix? So here's kind of an example to kind of do that rule of thumb, why polar and nonpolar don't mix. Here is an example where we've got water in the bottom of the beaker and we have an oil layer on the top. And oil is just a bunch of carbon and hydrogens for the most part. Or it's going to behave that way anyway. And remember we talked about when I was teaching you polar bonds and polar molecules, and we said, you can tell if a polar bond or if a covalent bond is polar by doing the difference in electronegativities. And when I had showed you on purpose, I had put on carbon and hydrogen so you could see that carbon and hydrogen have very similar electronegativities, so the bonds are not polar. So when you have a molecule that is mainly carbon and hydrogens, I want you to quickly look at that and be able to say, that's a nonpolar molecule. Water, I've just pounded into your head, is polar. Hopefully you never forget that. So the reason they don't mix is because if I wanted this oil to go down here into the water, I'm going to have to break these very strong hydrogen bonds. The water molecules are going to have to move away for the oil molecules to come down, and then they're going to have to form a new interaction. So let's see how it says it here. An oil layer floating on water. For a substance to dissolve, the water-water hydrogen bonds must be broken to make holes for the solute particles. However, those water-water interactions will break only if they're replaced by similar strong attractions with the solute. So if we did get the oil down there in the water, the attraction between the water and the oil is not going to be nearly as strong as a water to a water. So it's not going to let the oil come down and mix with that. Okay, so we finished one, which was talking about how likes dissolve likes and how that plays a role in whether you can expect a solute to dissolve. The second factor that affects the solubility is temperature. The solubility for most solids is going to increase as you increase the temperature, but the solubility of gases is going to decrease if you increase the temperature. So you got to keep that straight if I'm asking you a solubility question and I'm changing the temperature. Here is a slide that focuses on some of the solubility of solids. And if you notice, quite a bit of them are highly susceptible to changes in their solubility based upon temperature. So for example, glucose here, barely change the temperature and you can get quite a bit more glucose to dissolve. Same thing with the potassium nitrate. Sodium chloride, as I showed you on a previous table, you can increase the temperature and you can get a little bit more to dissolve, but sodium chloride's not super temperature dependent. Every once in a while, there's not very many, but there are some ionic compounds that the solubility actually decreases when you increase the temperature, but those are rare. So that's why I have the second bullet here that says the solubility of most solids increase with temperature. So for test purposes, that's what I want you to use. I want you to know that increase the temperature, you usually increase the solubility of a solid. All right, focusing on gases. Oh, actually, I have that slide coming up later. Changing gears to the third factor that's going to affect solubility is pressure. And we talk about this when we're trying to dissolve a gas in a liquid or a solid. So as the partial pressure of a gas above a liquid increases, the solubility of that gas is going to increase. So that should kind of make sense. Let's look at this very first picture here, our first pop can. If I want to get carbon dioxide to dissolve into my cola, what you're going to want to do is you're going to want to get the pressure of the gas above the cola very high. Because if we look at this picture here on the bottom, it should kind of make sense that the more molecules I have in the gas, the more molecules I can get to dissolve in the liquid. But what happens if you open this pop can? The minute you open the pop can, if you focus on the change in the gas particles on the top, you're going to have less gas particles on the top because they've escaped. And then that's going to cause the solubility, the gas particles inside the cola, to also leave. So the solubility of the gas is going to decrease when the temperature decreased. So as the partial pressure of a gas above the liquid increases, you can get more of it to dissolve. The solubility will also increase. So here's a learning check. Why could a bottle of carbonated drink possibly burst or explode when it's left out in the hot sun? So let's go back to this picture while we're talking about this. I have my pop can, I put it out in the hot sun, temperature is going to increase, and what do we know about the solubility of this gas when temperature increases? So from the previous slide, I had said solubility of solids increases as temperature increases, but solubility of gases decrease. So if we leave this pop can out in the sun, what happens is the solubility of this dissolved gas decreases, and so it comes out of the cola and into that space above, and pretty soon you're going to get so many molecules in that space above that it's going to burst. Same sort of explanation for the second one. Why do fish die in water that's too warm? It used to be really common to build factories on the edge of rivers, and the purpose for doing that is the machinery, as it gets hot, they would bring in cold water from the river to cool it down, and then they would dump that warmer water into the river. But what they found was that a lot of fish were dying in those regions because the temperature of the water was increasing. Well, what happens to the dissolved oxygen if the water increases? Well, the solubility of oxygen is going to decrease. So if the temperature is warmer, it's going to lose a lot of that dissolved oxygen gas, and then the fish won't have enough oxygen to breathe.